connect with the audience, right? So have a quick wrap up. What is printing? Not 3D. What is printing? Everybody is aware. What is printing? So should we be using English only, because I think it's getting recorded and has to go to some international platform? Is it, or can I go bilingual?
I think you can go bilingual because it's all supported by Guyana, which is Indian.
With due apologies to you, ma'am, you may not be able to follow Hindi or Punjabi, but I have to connect with this audience. Right?
So that's fine.
Students, are you comfortable with English alone, or should I go bilingual, or maybe use a little bit of Punjabi as well? Comfortable with English? Okay, good. Right, so printing everybody does? Oh, I just lost something. Anyhow, it's going on. You have printers at home, you have printers in the department, they do document printing, right? Just the same way we have got a 3D printer here before you, one. There are many 3D printing technologies. What 3D printer can do is it can make objects in 3 dimensions. So the documents that we print are in 2 dimensions on a piece of paper. Right? A 3D printer can actually print models like this. Now, some volunteer can come here and collect these from me. Please, ma'am. You can just pass on. Yeah. This is done in TPU, this is thermoplastic polyurethane. This one is in PLA, that is polylactic acid. You chemistry people can understand well. Right? Okay. So let's have a look at how we can do it. This is 3D printer. A similar one is getting printed right now. So before we get started, we should be knowing what we're talking about. So that's why I gave it to you. The one who is holding this black ring, just try to damage it, try to break it, the black one. इसको मेरे साइड पे कीजिए जितना चाहो, जोर लगा के, try to damage it. Can you damage it? Hold in your teeth or do whatever. It's quite tough. This is a property of thermoplastic polyurethane. The white one is relatively much fragile, but is otherwise dimensionally very accurate. That is done in polylactic acid. Okay, here's another one for you. You can try damaging this one for you. It's very tough. It's all done in this printer. Okay. So I have a small question for you students. If we have to publish a newspaper and make 1 million copies a day, what would you use for a newspaper? You would use a home printer or a commercial printer or a press? Press, of course. Why?
Multiplication.
Because the production rate is going to be very high. I want it to be dialogue, not a monologue, right? Okay. Can you expect a dialogue from you? Two-way communication, okay. And on the other extreme, you have to write a leave application. Should we go to press, make a block, then install in the press, and then tell him to spend the entire night making the block and then print just 1 copy? And then maybe you need a small proofreading, you make small change, then he has to make the block again. So that's not viable. So that is what we have to understand, the 4 V's first. That is, one is volume. Volume depends on demand. Newspapers are in huge demand, so you have to go to press. Right? When the variation is large, you have to look at some alternate. You cannot go to press with a customized document, invitation cards for example, where every name has to be printed. You can have the theme envelope printed, but then the addresses, they cannot be printed in the press. They have to be printed on using a printer. Earlier times they used to be handwritten, right? Then variation is concerning the change in the level of demand. So today something is in demand, tomorrow something else is going to be in demand, so you have to change the block in the press or maybe the tooling for the manufactured parts very, very frequently, right? So depending on variation in the product demand and variety, right? If let's say you have a production facility for making plastic parts and you're catering to 100 different customers, maybe 100 different clients for whom you're making the products. If one client cuts down the requirements today and another one increases the demand, then if we have a flexible manufacturing system, then you can tune to that. Right? But if you have just one kind of injection molding machine and one kind of tooling set, then your business will undergo fluctuations. Following? So variety and variation are important. Then the last one is visibility. That's the extent of customer connection. A very, very typical example of this is the Rolex watch company. They did wonderful business by connecting to the people. Right? You can watch a number of videos on YouTube or various OTT platforms concerning how Rolex had progressed in becoming a popular brand across the globe. And the challenges which they faced, they converted those challenges into opportunities. Those challenges were the World War I and World War II. So they converted all their challenges into opportunities, and today they are a brand to reckon. So that's the example I'm used to quote. Okay. So visibility is how well you can connect. How would you like if, let's say, your toothbrush, you keep it at some place in the home, and somebody else might happen to pick up yours, and you'll have to throw it away, right? Likewise for spoons in the mess. What if you have your names printed on them? Have you ever thought? Why have only Colgate printed on the toothbrush? Why not your name? Likewise for hairband or clips or whatever. All personal need items, if they have your name engraved or printed on them, then anyone will be warned, okay, this doesn't belong to me, even if the items are looking identical otherwise, right? So that way 3D printing can serve the purpose, because otherwise for just one hairband or one toothbrush you'll have to make fresh tooling which will cost you lakhs of rupees, and then making just one or two toothbrushes will not be viable. It will increase the cost of the product. That customized toothbrush through the conventional process may cost you something like 50,000 bucks. Otherwise, it will cost you just 50 bucks. So that's how the variety and demand, all that, right? It depends, it dictates the manufacturing process we're going to use. So the conventional processes are basically meant for large production volumes with very limited variety. But 3D printing can cater to very large variety but with a relatively limited volume. So understand these V's, variety and volume, right? Can we proceed ahead? So I'll just give you a brief outline about the conventional product development processes. There are basically three kinds of approaches by which we can develop a process. One is formative. You have a mold, you pour some molten material, maybe a metal or a plastic into that, and it forms the product. This first one. Then you have subtractive ones. Subtractive, what we do is we start with a bulk material, then we cut out the unwanted portion just as we do sculpting. A sculptor does sculpting as you have here before you, right? Remove the unwanted ones and then you are left with the desired product. And this third one is additive. This is the new entrant to this group, where the material is deposited just as required. You see, the first two have substantial wastages. The third one has very limited wastages. You just use just as much as is required, right? पहले में आपका मोल्ड वेस्ट हो रहा है, कुछ मटेरियल भी ऊपर से काटना पड़ा आपको. सेकंड वन में आप बहुत सारा कटिंग करके चिप्स फॉर्म में रिमूव करते हो, बट थर्ड में देयर इज हार्डली एनीथिंग टू रिमूव. सो द पार्ट्स विच यू होल्डिंग इन हैंड दे आर इन द जस्ट एज प्रिंटेड फॉर्म. हो सकता है आपको हल्की सी फिनिशिंग ब्लेड के साथ इन पे करनी पड़े, दैट्स इट. Even that can be taken care of by fine tuning the parameters. I don't know why this is not working. Anyhow. Okay, so this is one thing which I just wanted to show you how 3D printing can help. And it also signifies the designing approach using CAD software. So, ma'am, this is a weather station for precision agriculture application. So it has got sensors for temperature, humidity, and solar insolation, how much sunlight we're getting, and wind speed and all that. So this box is just to protect the components from atmosphere, and then expose them, maybe like humidity sensor has to be, right? It is mounted at the bottom, you can see. And then we have soil moisture sensor, and then a microcontroller and SIM808 module for transmitting the data via mobile network, via the GSM network. So it does all this, it records the parameters and then transmits to the cloud server at some prefixed interval of say a few seconds, around 15 seconds. It relays the information. So the data is getting collected. Now making this was a challenge in various ways, because once it is deployed, it's like sending a mission to the moon. You don't have access, or the access becomes very expensive. So this box is actually currently deployed in DCM's farms in Uttar Pradesh, and I can access the data. It's been there for 2 years now, right? And this is the actual one with all the wiring, and here's a comparison of the actual with the model, right? So assembling one box was a huge task. First you have to design the electronic circuit, you have to do the programming, and then you have to do the mechanical assembly. And mechanical assembly requires like drilling holes into a prefabricated box that you get on some platform like Amazon. And it used to take around 6 hours to assemble one box. Then what we did was, we resorted to a 3D printing solution. I'll just show it to you. This will give you a glimpse of the CAD approach. So this is in the CAD software. We modeled the entire box in the CAD. Then we modeled a drilling template that can be fixed at the bottom. So using an OHP marker, a permanent marker, we can just mark the position of these holes and then remove the plate and quickly drill. So what used to take around 6 hours now can be done in a matter of 15 minutes. So that is how 3D printing it comes in handy for making components with limited volumes, right? Now if we are to change the positioning of the boards in between, all we have to do is we have to just modify this bottom plate and then print a fresh one. That will take a couple of hours. No fixed tooling is required.
Which software is used?
This is a free and open source software. This is FreeCAD. FreeCAD. It's all free and open source. It's basically crowdsourced. You can download and install onto your machine. This is FreeCAD. I have a slide that will show you concerning various CAD software as well. The objective is to have you enabled today by the time you leave. Okay. Then the conventional process. This is concerning an agricultural tractor. We have a full-blown life-size sketch on the wall, the way we do all various checks. Then a wooden mock-up. Then the surface is scanned using a 3D scanner. Then some quality checks are performed on the surface, and then detailed designing is done. Now once the detailed designing is done, then we go for assembly modeling. All the various components as they're going to be fitted on the actual part, right? They are designed, and once that designing is done, then we go for making the mold. This is a conventional process. So this is a CNC machine. The pellet goes in, and the robotic arm will fix the required tool as per the CNC program, and then the cutting is performed. So the tools can be changed from the magazine as per the program, as per the requirement, and the cutting is performed. This is a conventional process. These machines usually will cost you something like 3 crore rupees. Then the per hour running cost is very high. In 3 shifts, 24 hours a day. Right? Then you have AMC, maintenance and all, then tooling cost, material cost, everything is very high. It's cutting a cavity right now. You can see in low alloy steel. Drilling operation. That is how most of your automobiles are manufactured. The tooling thereof. That is how it is made. Okay, done. Let's move to the next one. Now, after the tooling is done, we get the tooled up samples, the finished components, and here is an example of how the CAD model gets transformed into a physical component. But the cycle time is around 6 months from the model to the actual component. But once the 6 months the tooling is done, if you order them, okay, I need 3000 of them per day, you can get them. Right? That's a kind of production volume, just like newspaper printing. Right? But now the problem is the tooling will have would have costed you crores of rupees. So if you want a subtle change in design, you have to spend the same amount of money again, and the old tooling becomes scrap. What an idea. Okay, so this is the final product. So whenever companies they launch a new product, they have to go through this entire phase because the production volumes are high. Now, on the contrary, additive manufacturing's journey is different. You again start with idea, you again have CAD model, but from CAD model we don't go with the programs for tooling and the machines. We straight away go for an STL file, which is a test-related geometry file, and from there we make the NC part program, which goes to the 3D printer, and you get the printed output, just the way it is currently running a program, which is loaded into a small memory card here. Now, some of the tools and techniques, you people being from chemistry, you must be knowing about the term enantiomers. What are enantiomers? Can somebody tell? If you heard the term, optically active materials. What do they do? They are mirror images. What do they do to the light? They rotate the plane of polarization. So we'll do a small experiment here. I have got two linear polarizers with me, which are difficult to get these days. Okay. What I'll do is place it before my mobile. Can you see the mobile screen through this? You can. If I turn one of these, does it dim? It is actually circularly polarized, so it's not dimming. Anyhow, let's use unpolarized light. iPhone is a pain. How can you switch on some lights? Thank you, thank you. Now it's good. Can you see my eye? You can see me. Now let's turn it by 90 degrees. I'm gone. Turn it by another 90 degrees. Visible again. Right? So that is how a combination of a polarizer and analyzer, both are identical. It's just the placement. The first one is called as polarizer, the second one is called analyzer. So what polarizer does is it converts the unpolarized light into a plane polarized light. This is not a circular polarizer, this is a linear polarizer. The other one will stop the light. Now with this background, we can quickly have a recap of how the electromagnetic radiation works. So you have electric and magnetic fields. Then if you have conductors, closely spaced conductors, in the path of this beam, the electrical field along the conductors will get absorbed. Many books display this figure wrongly, right? So electrical field vector that was going upward can pass through this because it will not interact with these horizontal conductors. The horizontal component of the field vector, it will get absorbed because the electrons will start dancing to that, and it will absorb the horizontal component. And what you get is plane polarized light along the vertical plane. So it emerges. Now the next thing that we are going to have is we'll place a liquid crystal in between the polarizer and analyzer. You see, the polarizer, this is along one plane, this is at 90 degrees, the analyzer one. So the light comes, right, and then this liquid crystal, it rotates the plane of polarization of the light by 90 degrees, and then it can pass through the analyzer. But if you apply an electric field, turn the switch on, the liquid crystal molecules, they align as per the electric field, and they can no longer rotate the plane of polarization, and no light will pass through. So actually on your LCD displays, right, when the power is applied, the pixel becomes black. When there is no power, the pixel remains white. It's only the backlight that comes through, right? This is how the LCD works. Now Dr. Zain is using the same technology for polymerization 3D printers, polymerization resin-based 3D printers, because using this setup you can modulate the laser beam in a very, very quick succession, at a very high frequency. You can modulate the laser beam. The laser beam is made to follow raster scan using a combination of mirrors, and then the intensity of the beam is modulated, and depending on the intensity, the polymerization reaction will take place. So that is how, this is the working principle of the resin-based laser. Now for all these things to happen, you need a precision control of movement, and for that we make use of stepper motors. This is a little bit of engineering that comes into way, but I have tried to make it very, very easy for you to understand if just you know the basic physics of magnets, how they work. Will the audio play? मैं पहले तो ही क्या सी कि ਉਹ ਚ ਲਗਾ ਦਿਓ ਆਊਟ should I start? अच्छा no, there is no sound. Where is the audio going? अच्छा नहीं इतना नहीं आएगी because HDMI is connected, audio goes there.
नहीं सर ਇੱਥੇ भी ਆ ਗਈ
नहीं आएगी चलिए okay, good. Now let's make it full screen.
Does an automated milling machine move with such precision? It's all because of the stepper motor. What's special about the stepper motor is that
स्पीकर ऑन कर दो स्पीकर लगाया नहीं सर
they can control the angular position of the
I'll be
motor
honest.
without a
Just
closed
put
field.
all these things stuff. So stepper motor moves one step at a time.
Reluctance type of stepper motor works, which is the simplest one.
Leave it.
Later on, we will move to a highly accurate and commonly used motor type.
Okay.
This motor has 6 stator teeth and can be energized with 3 separate DC power sources. The motor is made of a stack of steel laminations. It has a different number of teeth than the rotor, 4 in this case. This is done intentionally so that only one pair of rotor teeth is aligned
Okay, I'll just explain it to you. What you have here is you have 3 pairs of coils, and the stator has got 4 teeth. Now, when you energize one pair, that uh, the corresponding tooth aligns with the coil, and the motor moves one step. When you go beyond,
What's special about the stepper motor is that it can control the angular position.
leave it. Right? So, by adjusting the number of teeth in the rotor and the stator, the angle can be adjusted. Right? All the commercial motors, as you are seeing in this printer, they all have a step size of 1.8 degrees because the magnetic poles of the rotor and the stator are designed that way. So you have 50 teeth on the rotor and 48 teeth on the stator, and their angular positions are so adjusted that when you energize one set of coils, then de-energize that and energize the next one, the motor turns by 1.8 degrees at a time. Then further resolution can be improved by making use of gears or pulleys, and you can get much finer resolution of movement. Another way of increasing the resolution is by using half stepping or micro stepping sequence. So अगर आप एक की बजाय 2 कॉइल्स को एनर्जाइज करोगे तो रोटर बीच में आके रुकेगा, so it will stop in between, and that way you can have half step. And if you continuously alter the magnetic field strength, the rotor will move slowly. Maybe you can have, like, instead of 2 you can have 4, 8, 16, 32, or maybe 64 or 128 or 256 microsteps in between. So that gives you very smooth and precise rotation. We call it as electronic gearing. So this is how the stepper is turning. This is full step. Then you can have half step. Now it will show you half step. So 2 coils will be energized simultaneously and the rotor will stop in between. So it is all based on the principle of least reluctance. So if you have done little bit of physical chemistry or physics, maybe you are aware about what reluctance is. It's basically concerning the path of the magnetic field. So this is how now the angle has been half. This is half stepping. The actual motor will have much larger number of teeth. So as you see in this video, this is the one. As you can see, this is a stepper motor here. A similar one. It can give you a step size of 1.8 degrees. So these are all working usually in the open loop system. So you just pass on a certain number of pulses to the motor, and then it executes that many steps, and so that much angle it turns. So with that you can have a precise control over the movement, a digital control. So this is how it goes. Now next thing, what makes it all possible is the access to open source hardware microcontrollers. So this one you're seeing here is an Arduino microcontroller. Then we have free and open source software. Ma'am, these are some of the packages that we use for 3D printing. So we have FreeCAD, as I've shown you. At the lower bottom corner we have OpenSCAD, that again is a free and open source software. And then on the top left you have PrintRun, that is for controlling the 3D printer. At the on the right side you have 3D Slicer. I'll show that to you. And in the lower bottom corner, bottom right, is FreeCAD. Yes, please.
To illustrate how accessible it is, would you be able to say how expensive an Arduino board is?
They are all free and open source.
Yeah. Now, but just to buy an Arduino board.
No. You don't need. They are like Wikipedia. They're crowdsourced.
Yeah, but the board itself, the hardware.
Hardware. Okay. The hardware can be open source but cannot be free.
Yeah, but how much?
This is Arduino Uno board. It costs around 500 rupees and around $10.
Yeah. So it's not.
It's not expensive. Then you have a bigger version, one is Arduino Mega, and that costs around 2 to 3 times this one, so around 1,500. So around $20-30. Mega is the one which is being used in this printer. And then you have other variants, Arduino Duo, That's double the cost, but with much larger resources. So this is a symbol for open source hardware, and the other symbol is for open source software, this green one. Okay, then continuing with the journey, all of you know how the laser works. So this is something which is required for, like you see, if you have done a polymeric filling for your teeth, what they do perform a light cure. Have you seen that? A blue light, they place the tip on they first fill it with a liquid resin, then they place the blue light, and the light cure takes place in a matter of a few seconds. So the same way you can form solid components out of a liquid resin by having a very precisely located laser beam. It sweeps across the surface and the intensity is modulated. So that is the working principle of laser based printing. So you have two technologies, and we have these platforms for buying these things these days: Amazon, RoboCraze, Electronics Comp, and so on. पूरा कर लिए पहला लेट बहुत हुई हैं, right? So 3D printing, when it came into being, it was used as a rapid prototyping option. 3D printers were very rare, they were very expensive, but with the passage of time, the entire process, it became much more user friendly, it became much cost effective, and the 3D printers, they became so common over the period of time that now you can stack multiple printers together to make a printing farm. You can control them using a centralized computer. You can have like 100, 200,000, 5,000 printers in a farm facility. Then you can just control what all parts are going to be made. So the amount of cycle time which a single printer takes to make parts, I've put it before you just to give you an idea. That cycle time is taken care of by having large number of printers working in parallel, right? So that takes us to the manufacturing based on 3D printing. So now if you have to change a design, you don't need to go for fresh tooling, you can straight away go for it, right? So these are the various processes: material jetting, binder jetting. I'll be quickly taking you through all this. So for material jetting, we'll play a video that will it's just like your inkjet printer, but the thing is, the sheet onto which the printing is taking place is going down layer by layer, and fresh polymer is being layered onto it. So this is how the 3D printing is done. So in each pass, it throws some material onto it through the fine nozzles. Just minute or so straight from the CAD model, just as you type a letter and then press Ctrl P, enter, same way you can do here. This is getting printed. There are many thousands of nozzles through which the material comes and gets deposited. Okay, I'll cut it short. Then we have binder jetting process. Here we make use of powder particles, and binder is thrown in the form of certain patterns layer by layer, then a fresh layer of powder particles, then again binder, another layer of particles, and binder. So this process doesn't use liquid material, only the liquid binder is there. So it is used for making cores for the mold making process for foundry. So these kind of sculpts, if you want to make these sculptures, you can do a 3D printing first, then put that 3D printed component into a sand mold, then pour molten metal. The 3D printed plastic will simply evaporate and the metal will take shape in the mold. So this kind of complex shapes can be 3D printed using this process. So you have a pass of resin binder, then a pass of powder, again a pass of resin binder, and so on. Then this is ultrasonic sheet lamination, not actually 3D printing process, but here you can use metal sheets for, and they are welded, bonded together using ultrasonic horns. So layer by layer you can make the shape. So this is a sonotrode which is doing the bonding. Then using the laser sintering we can have this powder bed fusion. So you have a layer of powder, then the laser fuses the powder particles at various locations. So layer by layer the process is completed. In principle this is very similar to resin printing, but this is using solid powder particles. Then we have photopolymerization. This has got probably the highest resolution among all the techniques, because the size of the pixel is decided by the cross section of the laser beam and the accuracy with which you can modulate. Dr. Hussain was just telling me that they have ordered a resin printer with a pixel size of 2 micrometers. It's very fine, but of course it will take very long cycle time to print one given component. So the laser beam is actually modulated with the help of liquid crystals. Then we have this FDM 3D printing, as the one we are having here. You can see it on your own when you get up. So here's a video of that. The filament is fed from the above and is getting melted in this small cubicle head there, because it has got 40-watt heater. So the molten filament is pushed through a small nozzle. You can have different sized nozzles. This one is 0.4 mm, and layer by layer the material gets deposited. So the printed components which I showed you, you can see they all have got layers. You can see on the side walls, they are all done layer by layer. So these are various geometries of FDM 3D printers. This one is following the Cartesian coordinate geometry, the one as you are seeing here on the table. Then we have delta printers. Did you watch the World Cup, no, so not World Cup, this Champions Trophy match between India and New Zealand on 9th, day before yesterday? Have you seen that camera which is suspended in the playground? It's following the same delta geometry. So using 3 ties, it can be taken to any location over the field. So this is the delta based geometry. So we have a vast choice of materials. You can see one black colored roll here. So you can have multicolored, multi-material rolls. There are dozens of types of materials available, each for their own application. Then we have various parameters like what kind of polymer blend, what color, some of the attributes, and the parameters can be divided into various broad categories. One is concerning the material category, then the printer settings, how much infill you want, how many surface layers you need, what is the pitch, the layer height kind of resolution. So some settings are pertaining to the printer, some settings are pertaining to the material, and some settings are pertaining to the printing process. So you have to just choose the best combination that gives you the desired result in terms of speed and accuracy. And you can make some customized parts. So it's a watch, wristwatch strap with name printed onto it. So then you can make parts which are not available in the market. I wanted to precisely control my telescope, so the brackets were not available, so I 3D printed them, right, to do the required job. Then you can have some impossible assemblies or components. Like here you have got a nut, but this screw is having caps on both the sides. So it's not possible to have something like this in the conventional process. एक तरफ से चूड़ी चढ़ाओगे उसकी, तो एक साइड खुली होनी चाहिए, right? But here you can, because you're printing the assembly itself, so you can have nut made layer by layer onto the bolt. Then these are some of the advantages of 3D printing. Here again you have got an impossible assembly. Then talking about the technology readiness levels, 3D printing is already at the TRL9. So it can perform all the required operations that we need to have in place. So if human race is to colonize other planets, 3D printing is going to be first and foremost thing to be deployed onto those platforms. So coming to the limitations and drawbacks, there are some technological aspects like speed, for example, and choice of materials. Another, in metals also, metal 3D printing has become possible. It is somewhat limited. Then coming to legal aspects, there have been instances when individuals have printed weapons using 3D printers, and those weapons, they can be printed at any place and then destroyed. So you can have a 3D printed pistol, maybe you can commit a crime and then destroy, and the worst thing is it doesn't leave any signature on the bullet marks. So that's the legal aspect. Then some of the recent landmarks, 3D printing of an entire engine, right? And L&T construction, it 3D printed a building. You can watch a video on YouTube. Then the future is concerning flexible and smart 3D printing firms. Flexible in terms of flexible manufacturing system, where they can take up a mix of product, a variable mix of products, what to make. Then of course, as I said, 3D printing farms on Moon and Mars, so that by the time you go there, you have the things ready. And then 4D printing is something which makes parts which change shape with time. That's a fourth dimension. So that's all from my side. If you have any questions, welcome to ask. Thank you. It is also finished. Yes.
So we have a lot of students here in the room that are working on the development of new materials. Do you have the capability to make your own filaments so that once they've made material in the lab, they may be able to 3D print something to test if they're
Yes, certainly that can be done. You just need a small extrusion type of machine which can also be made like DIY. Because the materials are not certainly going to be in large bulk, it's going to be small quantities. So we can make a filament of our own. The only thing is you just need to exercise some control on the diameter and the homogeneity. That's it.
Yeah. So for those of you that are working on material-based projects,
that's very nice.
think outside the box.
You can start working on materials, because all these materials that we're seeing around, they have also been developed by somebody. So you can extrude them into the form of a small filament and then wind it onto a roll and then use in a printer. That's a wonderful thing to do. So, any other questions before we part for tea? Thanks for joining. After this, we'll have a hands-on experience on FDM 3D printing. That's why I've brought the printer here, and I'll take you through various steps from modeling to printing. Right? Are you excited or not?
Yes, sir.
Doesn't seem to be so. Thank you.
Engineering isn't scary. You just have to jump into it.
Yes.
Yeah. It is very hands-on, and everybody played it as sandpits as a child.
Take it as a toy.
This is the new
You can
sandpit.
experiment with. And this is not something which has been brought for an exorbitant cost, and if something goes wrong, I'll not be able to repair it. It's all homegrown during the lockdown. So nothing can go wrong with it.
Well, if it goes wrong, you just go again.
Yeah, we can just
Fail
repair.
fast, fail
Yes, yes, yes. So with that, I think we should close, and then we'll come back for the hands-on training.
I think the training will be on this one.
Hmm?
The training, what she asked if the bag would be.
Yeah, training on this one. Yes, yes.
This one.
Okay. Anybody succeeded in damaging this component? You didn't try hard.
Try it.
You didn't try hard enough.
Then try with the teeth, most hardest.
It's very tough